Hi, and welcome to our third video on shear turbulence. What we're going to start doing now is looking at different places where you can find shear turbulence. And the first place we're going to look at is near the ground. We're going to talk about how the surface and the friction causes turbulence. So surface friction turbulence is a result from the air flowing over the ground. Specifically, we're going to look at a flat surface. If the Earth had some terrain relief, in other words, if it had large hills or mountains, then that would be more classified as mechanical turbulence. So the first thing that we're going to need to be concerned with is how the wind changes speed and direction with altitude. In other words, the vertical wind profile. Right at the surface of the Earth, the wind is not moving. Molecules of air are stuck to the surface. We call this viscosity, and viscosity results in friction. So the air molecules are not moving right at the surface, but just a few millimeters above the surface, the molecules of air start to move. They move with the wind. So you can see that in the lowest layers, this produces shear, where you have winds at the surface that are not moving, and then moving a few millimeters above. And as you go up through the atmosphere, the wind speed increases with height. So much so that in the lowest 500 feet AGL, the wind speed increases exponentially, although the wind direction does not change all that much in the lowest 500 feet above the ground. If you tend to think of that, whenever you come in for a landing and the wind is straight down the runway at the surface, usually on final approach, the wind is going to be also coming towards your nose. In other words, you'll have a headwind. You don't see a big change in wind speed in the lowest 500 feet. If you do, then crosswind landings would happen every day. Above 500 feet, the wind also does increase with height throughout the depth of the boundary layer, but it increases more slowly above 500 feet. But it does change direction, and that's what this diagram tries to show, is that down at the surface the winds are rather light, only about 10 knots, and they're blowing across the isobars. But at higher altitude, 3,000 or 4,000 feet, AGL or MSL for that matter, the winds are more or less flowing parallel to the isobars, and they're much stronger. So the wind turns clockwise with height as a result of friction in the lowest layers of the atmosphere. So now let's try and look at some of the characteristics of turbulence caused by surface friction. And it's pretty obvious that with this strong shear, you're going to have strong eddies near the surface as a result of the shearing stresses in the lower layers of the atmosphere. And remember, that also is modified by the amount of stability in the atmosphere. And these eddies result in the fluctuations that you see with the anemometer, or in other words, the windsock. If there's strong enough wind shear to produce eddies, as these eddies move over the windsock and move over the anemometer, you will have gusting conditions. The eddies travel with the wind and they move downwind. As long as there's strong shear in the lowest layers, these eddies continue to be produced and they move with the wind. The lowest layer of the atmosphere where you have these eddies being produced is called the boundary layer. And by definition, the boundary layer is a layer in which you have friction that is affecting the wind. There are many different factors that determine the depth of the boundary layer. Probably the most important factor, though, is the wind speed. Strong wind speeds tend to produce a very thick boundary layer. Weaker wind speeds produce a rather thin boundary layer. Another thing is also stability. If the atmosphere is very stable, then you'll have a very shallow boundary layer. However, if it's unstable, it tends to be thicker. Think about North Dakota in the wintertime. If there's snow on the ground, then the air tends to be rather stable unless you have very strong winds, and then that produces turbulence through a very deep layer of the atmosphere. So typically the boundary layer can range from 500 to 5,000 feet AGL. During the wintertime, on a light wind day, it might only be 500 feet. But in North Dakota during the summertime, as we get thermals, the atmosphere is more unstable, and perhaps if you have a little bit more wind, the depth of the boundary layer will be much greater, more like 5,000 feet AGL. And it's pretty obvious that the closer you are to the ground, the closer you are to the region that's generating the eddies, the more turbulence you will have. So down low, you tend to get more turbulence if there's strong shear, and as you climb higher, you'll get a smoother ride. The Air Force has a forecasting rule of thumb for shear in the lowest layers of the atmosphere and surface friction turbulence, and that is, if the wind speeds over a flat surface are more than 30 knots, then you can expect moderate or greater turbulence. Another thing that you can do is use the gust factor. The gust factor is the difference between the peak wind speed and the sustained or average wind speed. In this example, in this METAR, the winds are 210 at 16, gusting to 24. If you take the difference, 24 minus 16 gives you 8, and that is your gust factor. We'll use the gust factor later on in determining our final approach speed under windy conditions. So that ends our discussion on the characteristics of surface friction turbulence. In the next video, we'll talk about how to fly when there is strong shears in the lowest layers of the atmosphere and you're getting turbulence because of surface friction.